The latest project I've been working on is a new instrument, which I'm referring to as the electronic valve instrument. It's based on an existing design known as the new EVI, made by Berglund Instruments. I'll leave a link in the description so you can check it out if you like. The difference between this instrument and the electronic wind instrument, which I presented in my last video, is that this one is played more like a trumpet. As you can see, it's got only 3 finger pads instead of the full clarinet finger pattern. These extra buttons around the side are for fancy things like trills and other special effects. Another difference with the way that this is played when compared to the electronic wind instrument is that the octaves are selected using this rotary drum on the bottom. You hold this with your left hand and you turn it to the position that correlates with a given octave. To measure the angle of the drum, I'm building a rotary encoder, which is a device that allows you to measure angle based on a pair of light gates and a little bit of digital coding. That will be the main topic of this video, where I'll show you some CAD models, I'll show you the design, and I'll show you the thing working in the end. Here you can see the side view of the instrument. You can see the rotating drum, and also I've got some little pitch bend levers here, so you can slide your thumb back and forth and adjust the pitch of the note that you're playing. That'll be the subject of a later video, as I haven't quite worked out the design for it yet. On the bottom you can also see this little panel. This is just a little screen, some selection buttons, a headphone jack, a USB port and a MIDI port. This is so that you can change the settings of the device, such as the mode you're operating in, where the output is coming from, and things like the volume, the sensitivity and other stuff like that. I'll also make a video about that at some point. Another thing that you might have noticed is this kind of circular thing in the middle between the pitch bend levers. This will be a small hole with a little lever coming through it which can be used for vibrato, instead of having to rely on the coarse adjustment of the pitch bend levers. And now onto the main feature, the rotary encoder. The way this works is you have a disc spinning on an axis. The disc has holes in it which cover and uncover the path of 2 light gates. Depending on which light gates are covered, you can tell what angle the disc is at. If we take the pattern that's drawn on the disc and we unfold it into a straight line, you can see what's going on here. If we take the black area as a mask and these white squares as holes, you can see that when you move from one segment to the next, only one of them changes in each jump. This is referred to as a Hamming distance of 1, and is a property of this code, which is called the 2-bit gray code. This is a common way of encoding a sequence, as it prevents the error that might be caused if 2 bits change at the same time. To turn all this theory into practice, this is what I initially came up with. Here you can see me rotating the disc, and you can see the pattern of grey code through the little holes that are where the light gates are going to go. In the end, I changed it up a little bit and went for a slightly more complicated design. It still works the same way, but I've moved one of the light gates over to the other side of the central axis. This allows me to fit it in a slightly narrower space inside the body of the EVI. I've also added a ball bearing and a little bushing to this design. These are meant to make it run a little bit smoother so it feels better when you twist it. As before, you can see the pattern of grey code through the light gate holes. On the completed version, there'll be an LED in the top hole and an LDR in the bottom hole. LDR stands for Light Dependent Resistor, and is a form of sensor that can be used to detect the changes in the light intensity coming through the light gate. The circuit board at the front of the encoder is modelled using measurements taken from the physical circuit that I built on a piece of strip board. It's a bit time consuming to do it this way, but it really does prevent lots of errors when you get conflicting parts and things bumping off each other. It's kind of a case of the 6 Ps. Proper preparation prevents piss poor performance, and you can see here I'm implementing the same strategy, planning out the perf board before I scrape away some tracks and ruin it. Something key to getting good solder joints is to clean your board and also use lots of flux. You gotta remember though, if you're gonna flux, wear protection. Maybe this is me just making excuses, but I think my terrible soldering in this case was due to the perf board that I was using. It seems to have a very weak glue or something that sticks the copper traces onto the fiberglass, and when you heat it up, they actually pop off sometimes and make little cavities in the solder. Enough excuses though, here's the final thing working. You can see I'm covering up the 2 little LDRs in turn, and the LED indicator at the output is showing whether they're triggering or not. The circuit that really makes the rotary encoder work is called a comparator. It's based around the op-amp, also known as an operational amplifier. Essentially what it does is it takes the input from its inverting and non-inverting terminals, subtracts them, and then multiplies them by a really big value. This value A is referred to as the gain. By adding a few different resistors on the input, we can turn this into something called a comparator, which is used to compare the 2 inputs and see which is larger. On this leg of the input, you can see the LDR which I mentioned earlier. Over here, we have a variable resistor which can be adjusted to tune the response so that you can get the circuit to trigger at different light intensities. I'm currently feeding this output into an LED so you can see what the circuit's doing, but eventually it's going to be piped into the input of the microcontroller that's powering the EVI. The LDR, as its name suggests, has a resistance value which changes depending on the light intensity that falls on it. Thanks to my physics high school teacher, I have these handy mnemonics to remember which direction the resistance goes depending on the light intensity. This is for an LDR, and this is for a thermistor. LURD and TURD. Light up, resistance down, temperature up, resistance down. In the case of this comparator circuit, when the light intensity on the LDR increases, i.e. when there's a gap in the mask on the rotary encoder, the resistance goes down, which lowers the voltage here, which is on the inverting input to the op-amp. If you look at that equation again, what this means is that at a certain point when the light is bright enough, the inverting input voltage will drop below the voltage of the non-inverting input. The op-amp will then amplify the difference of the two and give an output that is a high signal. It's good to note that for this circuit to work properly, you have to assume that A, the gain, is really big. You can see the input-output characteristic of the op-amp here, when the gain is not very high. As you can see, there's sort of a gentle slope from when the inverting input voltage becomes lower than the non-inverting input voltage. This doesn't give us a very good switching ability, because it takes quite a long time for the output to change. On the other hand, in practice, when A is really big, usually on the order of about 10 to the 5, so 100,000, the difference between the inverting and non-inverting input voltages is magnified by a really large gain, and you get a pretty much instantaneous switching. There is a little bit of a grey zone in the middle, but for the most part it's pretty much negligible. Op-amps are really magical. They're useful for loads of different things, and this is really just one application. They're also great for measuring, filtering, performing other logic operations, and adding stuff. In future projects, you might well see them popping up again and again because they're such useful little chips. When you squash together a few hours of 3D printing, with some soldering and a little bit of electronics, you get this thing. Somehow I've managed to make it look kind of neat and kind of messy at the same time, but it seems to work, so I'm happy. I'm looking forward to putting this in the EVI to see if it works properly. And that concludes this phase of the project. If you enjoyed the video, please do drop a like, subscribe, and maybe leave a comment to let me know what you think. The next video is going to be covering the back panel for all the inputs and outputs of the EVI. I'm also going to have a look at the touch sensing system using the MPR121 touch sensor chip. That's all for now though, so take care, and I'll see you in the next installment.